You're going to want to start by pausing the video and copying down this whiteboard. Pause the video and copy. We're starting a brand new unit today, and one of the we're going to be looking at the most interesting of the subatomic particles. There's 3 subatomic particles. Which one do you think I think is most interesting? The electrons are, all right? The protons and the neutrons are stuck there in the nucleus. And you can study that. It's called nuclear chemistry if you do so. But the electrons have the widest range of interesting things that they do, all right? They're spinning around the outside. So whenever 2 atoms come near each other, it's the electrons that interact first, making them the most fun to study. They're going to dictate things like bonding and chemical reactions. Bless you. As soon as I pressed play, you felt it coming, didn't you? I lost my train of thought. So the electrons are going to dictate a lot of stuff down the line as we study chemistry. However, the very first thing that we're going to look at for electrons is something a little less expected. Electrons have the ability to produce light. And light is kind of a funny thing to study in chemistry. Who can tell me why? What does light not have that everything else that we study in here does have? Mass and volume. Light is not matter. But since our friends, the electrons, have the ability to produce light, we are going to spend 2 days, yeah, this is a 2-day lecture, looking at electrons' connection to light. So let's look at light as a whole first. Write this down, please. What I have here is a basic wave. All right, I'm going to call it a light wave, but it could be like a sound wave. But we're gonna equate it to wave, and I just want to show you a couple different things that exist in my light here. One of the things is this. Anybody know what the names of these distances are? Can't even really see. Well, I guess we kind of get to the end of that one. Anybody know what those distances are called when looking at the distance between waves? Wavelengths. Those are wavelengths. So we actually represent those with a funny little symbol called a lambda that you copy down on the other whiteboard. But that's what he looks like. He's a little squiggle with a leg. And that means wavelength. What do you notice about the wavelengths if you compare them together here? Let's go to 4-1. What do you notice about the wavelengths? They are getting larger. As you go from left to right, you can see that the lengths are getting larger. These are shorter wavelengths, and these are longer wavelengths. Now, with this idea, there's a couple other parts of a wave that we can look at. Some other variables. One of them is frequency. If you look at the other whiteboards, you can see that V stands for frequency. You've already written it down. Can anybody tell me what frequency refers to? Y'all am I quiet? I'm going to quit recording in this class. All right, let's go to 3-6. What does it mean if something is frequent? It happens often, all right? If something has a high frequency, it means it happens often, all right? Like a lot of y'all breathe frequently, all right? But you eat less frequently. You only eat a few times a day. You breathe more than 3 times a day, all right? So if something has a high frequency, it happens more often. So looking at my picture here, do you think the left or right side of the board has a higher frequency? The left. These waves down here are happening more often. I pointed that blue arrow in the direction that frequency increases. So you can already start to draw some conclusions from my little picture of the wave here, that the shorter the wavelength, the higher the frequency. All right, the shorter wavelengths have waves that are happening more often. There's another variable we can look at, which is energy. And energy actually works in the same trend as your frequency. It also increases towards the side with the smaller wavelengths. And the idea is the more often a wave is happening, the more energy it's taking to do it. Whereas these guys down here have much bigger wavelengths, and it doesn't take so much energy to do those because they're so less frequent. Now, these ideas are basically just for any wave. I'm telling you that the reason we're looking at this is because electrons produce light. So to make this a connect to light, I can add a little something for you. What are those letters along the bottom? Colors, right? Some people say rainbow. They're the electromagnetic spectrum. Those letters on the bottom are the electromagnetic spectrum. But as most of you know, they're simply, go with me, the colors of the rainbow, right? They really exist in these locations based off this wave theory that I'm showing you, which means you can already answer some questions about the way the colors that electrons will give off will tell you or draw conclusions about the electrons themselves. So let's go to 5-5. Not 5-5. Let's go to 4-1. Seriously? I don't know why it's picking on you. Which color of the spectrum has the lowest frequency? Red has the lowest frequency because he's way over here where the wavelengths are very, very large. Let's head to 1-6. 6-1. Hi, 6-1. Which of the following has more energy? Blue or yellow? Go again. Energy is increasing this way. Blue or yellow? Which one has more energy? The blue. All right. Further to the left of the spectrum, where the wavelengths are shorter. So you see some of the basic light questions that we could figure out on connecting color to these things. Actually, you had a parent or guardian at one time in your life teach you some of this on accident, because you may have once had someone tell you that there's a certain color of fire that you should stay away from. Which color was worse? Blue fire. All right. You might have been told to stay away from the blue fire because it would hurt you more. And whoever told you that was absolutely right, because blue fire has more energy than the orange fire that you're used to seeing. It truly is hotter because of this whole idea, and would do more damage if you touch it. I've got two different ways to show you electrons' abilities to produce these light and give you these conclusions. One of them is fun, and we're going to do that on Friday. Friday's the fun day. We're going to go to a dark room, and I'll show you some light stuff. You'll like that. Today's less fun. Today, I want to apply mathematics to this idea so that you can see that they are connected in an interesting way. Let's take a look at a few of the things on this board over here. You'll notice that wavelength, energy, and frequency are all hanging out. And we just got done talking about all of those along with their variables. I also want to show you that their units that we use to measure them are listed on this board. Wavelength in meters, energy in joules, and frequency in hertz, which is what happens if you drop a hammer on your foot. It's good stuff. Anyway, I also want to point out that these units I have written here are the only units that can go into the equations that we're going to use. That's really important because if you run into a problem that gives you anything that's not these, like if you run into something, for example, that says millimeters, well, that's not the same as meters, and you'd have to do an extra step. So you might want to make a note somewhere that these three units are essential because those are the only units that can go in, and they're the only units that will come out of our math that we're going to do. Some other interesting things on my whiteboard, you'll notice the speed of light. All right, you've probably heard the phrase speed of light before, but never messed with it mathematically too much. Do y'all think light travels fast or slow? Yeah, kind of super fast. All right, and here's the number. All right, what's the E stand for right there? No. Times 10. All right, remember the capital E's from previous units? All right, E stands for times 10. It's scientific notation. All right, so 3 times 10 to the 8th power meters per second, which means you'd slide that decimal out 8 times, is how fast light travels. Super fast, don't race light. All right? Another thing we'll be dealing with is Planck's constant. Planck is a scientist given credit for measuring the amount of energy in like a flash of light. There's better vocab for that we'll talk about on Friday. But for now, Planck measured how much energy there is in just a flash of light. Look at that number. Is that a really big number or a really small number? That's the smallest number that I've ever shown you in this room. It says to slide that decimal to the left 34 times. That's a bunch of zeros. Guys, the amount of energy in a flash of light is very small, very minuscule. And it's actually really important that it is. What are we surrounded by right now? Light. We're surrounded by a ton of light. And if it all had a high amounts of energy, well, we would be kind of dancing our way through life because we'd be getting shocked all the time. So it's really important that light contains such a small amount of energy when produced in a flash. But this is the constant value that we'll be using in our calculations. Now, do you see the turquoise stars? I've put turquoise stars next to the 4 bits of information that I will give you on the test. In other words, you don't have to memorize the speed of light. You don't have to memorize Planck's constant. You also do not have to memorize the first black equation and the first blue equation. However, you do need to be aware of your units here. And you need to know the other 3 equations. Now, if you went to a pre-algebra class once upon a time, I've given you a warning like this before, you can turn these into these by manipulating the variables. Right, I'm going to give you that one, so if you can move the stuff around, you can get the other 2. But if you don't trust your pre-algebra, well, then memorize them, or whatever. Also, I've given you some conversion factors down here. I've already taught you this stuff. You know how to convert nanometers to meters. We did that in Unit 1. But if you don't trust yourself again on something you've already learned, then you can memorize those factors as well. Write this down as our first problem. Pause the video if you need to. So this problem wants to know how much energy exists when a wave is happening that often. I can tell that by the word frequency. We're going to solve these in the same way we solve all math in here, which is by simply starting by extracting the number. So you write everything I do. Let's take a look. The first thing I see is 9.13 E7. Now you can write times 10 if you want to. That's what the E stands for when it's in the middle of a number. But that's just more writing, but whatever. Hertz. Hey, what's the variable for Hertz? Look back at that other whiteboard over there. What does Hertz tell us? Frequency. Frequency. And what's the variable for frequency? The letter V. So you should be able to get all of that from that other board. Is Hertz an acceptable unit? Remember what I said. All of our units have to match the units over there. Is Hertz a good unit? It is. All right, we have Hertz. All right, we've got meters and we got joules. My brain's went blank. All right, Hertz is good, so there's no extra step here. All right, well, that's all the numbers that are in the problem. What does this problem want us to find? Try again. Determine the energy. All right, we already have frequency. We know frequency. If we want us to find frequency, we'd be done. All right, it says determine the energy. Energy is represented by a capital E. So here's what we want to do. We want to find an equation that solves for energy. It'll say E equals something. And on the something side, there's a V over there. It uses frequency to solve for energy. So take a look at your equations. Do you see one that does that? Look, here it is. E equals HV. We've got an equation that says E equals HV. That will solve this problem and help us find how much energy exists at this wavelength. And from here, it's just a plug and chug. E equals, do we know H? We always know H. H is Planck's constant. It's written over there on the board for you. And you don't have to memorize it. 6.63 E negative 34. The amount of energy in a flash of light. That's a constant number. And that's the H. Multiplied by frequency. Do we know V? Yeah, it's a given number from the problem. 9.13 E7. Now, we haven't typed numbers into scientific numbers in the calculator for a while, so if you need me to reteach you the buttons to push, I can. I'm going to open parentheses and go 6.63. Remember, to make the big E show up, you want to hit the second button, and then the button above the 7. And that will make the E appear. And then your calculator is awaiting an exponent, in this case, negative 34. Don't push minus 34. Those are two very different things. The negative button is at the very bottom of the calculator. And multiply that by 9.13 E7. If you need issues, or if you know that you're not able to find the E, please call me over now. 4? No, 5-4. 3-2. 2-3. What is your answer? Perfect. And she even took sig figs into account. Notice how my given value has 3 sig figs, the 9.13. Remember, significant numbers don't take the scientific part into account. So the answer that she gave was 6.05 E negative 26. Anybody know the units of that answer? We found energy, so what's the units of energy? Joules. Hey, it was better than no answer. Anybody get a different number and they don't know why? Let's try another one. This will be our second problem. Let's start off by pulling the given number out. I see 907 nanometers is the only value given in the problem. Who can tell me what nanometers is units of over there? It's wavelength. Now, your eyes are a little confused because you don't see nanometers, you see meters. But it is a length. It is wavelength. What you're noticing is we have a problem with the units. Remember, the only acceptable units are the ones listed over there, and this problem is starting us with nanometers. We need to change that to meters right away, which again, we'll call on one of our old scales. I need 907 nanometers to change into meters so that we can use it in our problem. If I want these nanometers to go away, where else do I put the unit? The bottom. That will make nanometers disappear, and now I can convert it into the unit that I want. Now, if you look at the other whiteboard, you'll see the conversion factor that we'll use to do this. You just put those numbers into the respective squares. It says that 1 nanometer is equal to 1 e times 10 to the negative 9 meters. And this will do the conversion so that we can start the problem. Remember, you multiply across the top and divide by the bottom, and some of y'all will be able to do this conversion without drawing out a grid. That's fine. This is just how I have to teach it. And now we can report a number in meters. Now, your calculator likely spit out a number that says 0.0000 and some stuff. All right, which is fine. You can use that number. I like to use this number better. 9.07 e negative 7, which is likely the exact same number that you got with all those zeros. You can use the zeros number, or you can convert it to mine. They're the same number. But now we've got meters, and now we can continue the problem. Any questions on that conversion? All right, let's take a look at what this question wants us to find. Look up there. What does it say to calculate? Frequency. We want to find frequency. And again, if you look at the other whiteboard, the variable for frequency is V. So what we want then is an equation that says V equals, so it's solving for V, and then has that lambda, that wavelength sign, on the other side. Look over there, see if you find one. Do you see one? There it is. V equals, and there's that lambda sign. V equals C over wavelength is the equation to analyze this light. So let's plug in, Shug. V equals, do we have a value for C? We always have a value for C. It's the speed of light. Just go grab it from over there. 3e8. 3 times 10 to the 8th power is C. Do we have a value for wavelength? It's the meters that we converted earlier in the problem. 9.07 e negative 7. Any questions about my setup? See if you can get the answer. Josh, what'd your calculator say?
3.307.
All right. Keep going. There's an exponent there at the very end. Times 10 to the 14. Now, to round it to our sig figs, though, all right, we want exactly 3 sig figs. So 3.31 E14 is what I get. 3.31 E14. Can anybody tell me the units of that answer? Hertz, because we found frequency, and frequency is measured in hertz. Yes, sir. Why would it be 1 sig fig? Whenever you're choosing your sig fig, it's going to be based solely off the given information. Constant values that you use as part of the equation will not determine sig figs. Good question.